VC Chemistry, Unit 4, using infrared spectroscopy to identify functional groups. Okay, so when we look at a IR spectroscopy, there are some of the words that we use to describe a particular absorption. When the peak is really deep, that's a strong absorption. So then therefore you will have medium and weak. Sometimes the absorption band is rather broad, and sometimes it could be narrow. These are all very important features in a IR spectrum. Okay. So as we talked about before, when we use IR, we're mostly really looking at the regions where the absorption occurs, and use that with the assistance of an empirical formula or a molecular formula that was already given to us. Then we try to pinpoint a particular single bond or double bond or triple bond that actually exists in this particular molecule. Okay? And again, the lower region is the fingerprint region. It is not very useful. There commonly will be a lot of absorptions here. Okay? So even though the carbon-chlorine and carbon-oxygen bond is given in data book, but we don't normally use them. Okay. The first spectrum that we must tattoo to our brain is that of an ester. So ester functional group is a carbonyl group with a carbon-oxygen single bond. Okay? So a particular ester spectroscopy in IR will look somewhat like this. You will see that there is a strong absorption between somewhere around 1700 to 1800. Okay? That might vary depending on where the ester is, namely like what are the groups that's connected to the particular ester functional group. Okay? But normally around 1700 to 1800, that is due to the carbon-oxygen double bond. And you notice that in the higher end of the spectrum, there is a medium dip. That is due to a carbon-hydrogen absorption that all organic compounds have. So basically, for all organic compounds, around above 2800 to about 3000 or 3200, you should expect to see some kind of absorption in IR. So how about the carbon-oxygen single bond that help us to confirm it's an ester? Because ketones also have a carbonyl group, should also have a dip, and then aldehyde will also have a dip. Well, sadly, carbon-oxygen single bond is in this fingerprint region, so it's not really useful to us. That's why I said that IR alone cannot help us to pinpoint exactly what a molecule looks like. We have to use other information. A lot of times we really just use different regions to help us to identify a very characteristic kind of single bond or double bond. Okay? That's the ester. Now let's look at an alcohol. Again, the fingerprint region we don't really have to pay attention to, but here the alcohol has a extra absorption at a higher end that is due to the hydroxyl group, the OH bond. And that's really high, that's above 3200. And you notice that next to it there is also an independent, relatively strong absorption that's around 2800. That's because of the hydrogen-carbon bond, so hydrocarbon absorption here. And when a molecule only has a hydroxyl group, then these two absorption peaks are independent. They do not merge together. So what happens when there is a hydroxyl group bonded right next to a carbonyl group then? Then it becomes an ester. And this absorption pattern is very unique to a carboxylic acid. So first of all, you'd notice that there is an absorption around 1700. That's the carbonyl group, right? But there's also a very strong and also broad absorption at 32 to 3600. Yeah, that is the hydroxyl group. But that's not unique enough. What's even more is that notice that there seems to be a merging of two absorptions here, right? It seems that someone was here, and they sort of merged. Okay, so the carbon-hydrogen group, when in the spectrum of a carboxylic acid, the CH absorption band is often overshadowed by the hydroxyl group here. So this peak, due to the strong absorption of the hydroxyl group, this peak sort of merged into it and become a one fat band. And it will only happen when the hydroxyl group is right next to a carbonyl group. Yeah? So only carboxylic acid will have this kind of overshadowing effect at the higher end of the spectrum. And therefore, when we see this kind of pattern, we have to go straight to find that carbonyl group absorption and therefore confirm that this compound is a carboxylic acid. Now let's practice. These two IR spectrum, which one belongs to methylethanoate and which one belongs to propanoic acid? Okay? Well, here I have already marked out the particular bond responsible for a particular dip here. So you will see that here the top graph has again, very unique overshadowing effect of the CH absorption here and the OH absorption here. Okay? And they merge together. This will only happen when the OH is connected to the carbonyl group straight away. So we do have a carbonyl group here, so this can only be the graph for an acid. And looking at the bottom group, we do have a carbonyl absorption at the 1700 to 1800 band. Then we really have nothing else but a hydrogen-carbon, sort of hydrocarbon medium peak here. So this is unique to a ester. Okay. Since we don't really have other choice, we don't really have to distinguish if this is an aldehyde or ketone. We're really just choosing between an ester and a propanoic acid. Then we can basically be sure that this is the graph of an ester.